Welcome to the video for the gas law station lab demos. Today in class we are going to be looking at a bunch of different demos through some YouTube videos. Now you'll have a sheet that you should have out in front of you right now. It should say gas law station labs on the top of it. And this is going to be used not only for the demos today but also for your labs next week. Here's a copy of the sheet that we're going to be going through in class today, and on the left hand side here you can see the name of the demos that we're going to be doing in class today, and then after this is some observations and drawings that we need to do. So if you look over here in this box here, you're going to put observations before and during the experiment, and then you're going to be including gas law names and the gas law equation that accompanies that name. And there are a couple of questions that go along with each of the gas laws, and we're going to be expecting you to answer those questions as well. So we're going to be going through those in the next few slides. Okay, the first experiment that you're going to be watching is called the bell jar demo. During this experiment, and you'll hear this as the person on YouTube goes through with it as well, but during this experiment what's happening is you have a jar, and we're going to be putting marshmallows in that jar and taking the pressure out of the jar. So we're basically going to be removing all air pressure from the jar, and we're going to see what that does to the volume. So now you can pause this video and go to the marshmallow demo on YouTube. Welcome back. So you just got done watching the marshmallow experiment, and what happened was in the video we basically decreased all the pressure from the marshmallow's environment, and when we do that the volume of the marshmallow is increasing because there's nothing to hold the marshmallow in place anymore. So when we draw this in our picture on the left hand side here, you should have something with equal pressures. So these arrows on the inside and outside right here should be equal, so it's being supported. Now after the experiment, the balloon or the marshmallows are expanding in size, and why that's happening is because the pressure's inside here, you notice the arrow's bigger, it's pushing out greater than the atmosphere is pushing in. The gas law then that goes with this is Boyle's law, and the gas law equation is P1 V1 equals P2 V2. The last thing that we're going to do here is you have a problem. It says a marshmallow peep is at 42 centimeters cubed at 1 atmosphere. And what is the size of the peep at 0.5 atmospheres? So I'd like you to pause it just for a minute here, and everybody in class can have a chance to work on this. Okay, so how we set up with this problem is we would have the 1 atmosphere times the 42 centimeters cubed equals the 0.5 atmospheres times V2. So we'd multiply 1.0 atmospheres times 42 and divide by 0.5, telling us our V2 is 84 centimeters cubed. Alright, the next video that we're going to watch, we're going to see what happens when somebody puts balloons into liquid nitrogen. So we're going to be greatly decreasing the temperature of the air in these balloons, and then seeing what happens after we take them back out. But what I really want you to focus on here is what happens as they're going into the liquid nitrogen, or what they look like just after they come out and the temperature's been taken down. So pause for a minute and let's watch the 4-minute liquid nitrogen video. Alright, so now we want to draw a picture of what happened to these balloons during the experiment. So our first picture here on the left should show our gases, or our particles inside are moving at a pretty high speed, and they're able to fill the whole size of this balloon. Now after we put them in the liquid nitrogen, what's going to happen is that they're going to start slowing down, moving much slower, so they're colliding with the outside of the balloon much less. So our balloon gets kind of shriveled up and it actually shrinks in volume, and that's because the molecules aren't moving as much because their temperature is less. So that would be this picture right here. Take a second and just draw those before and during experiment pictures out. Next, we want to say what law this applies with. The law that this one is Charles' law. And the gas law equation for this is V1 over T1 equals V2 over T2. We got another problem to do here. So we take a minute and go through this one as well. It says a basketball is inflated to a volume of 4.0 liters outdoors at 15 degrees Celsius. Then the ball is taken inside the gym at room temperature, 25 degrees Celsius. What is the new volume of the ball, assuming no change in pressure? So we can pause, take a minute to work on this one. All right, going through, here we'd have V1 over our T1 equals our V2 over our T2. And notice here we have 288 and 298. That's because our 15 degrees Celsius and 25 degrees Celsius needs to get converted into Kelvin. If we don't do that, we're going to get a drastically different answer. And then all we're doing here is cross multiplying my 4 liters by 298 here, and then dividing by the 288. And that's going to give us a value of 4.14 liters. So not by a ton, but it does increase the size. All right, for the next experiment, we're going to be watching what happens when we put a bar of ivory soap in a microwave. And so we're thinking again about kinetic energy here and what happens when we are adding heat or kinetic energy to the molecules, and then what happens to the volume because of that. So as you watch this video, just be thinking about those things and trying to draw over here what's happening during. So we can pause now and go to the soap in the microwave demo. Okay, so thinking about the things that we just saw during the demo, we should have two pictures here. In our first picture is on the left here, we should have a bar of ivory soap. And in this picture, our molecules are at room temperature, and the soap has a very constant shape. Now, when we put this in the microwave, our kinetic energy of our molecules went way, way, way up. So that's what this arrow is showing us up here, which causes the temperature of the molecules to go way up, and it causes the volume to go up. Now, this is because they have increased kinetic energy, and they're bouncing off the sides here, the inside of the soap, more and more and more, causing the soap to expand in this case. This is another example of Charles' law. So the equation again is V1 over T1 equals V2 over T2. So I'll give you a minute just to finish up and get some of that stuff written in here. Okay, once again, we have another equation that goes along with this law. Now, there's a couple things that are happening here, so we just need to be paying attention a little bit. First of all, it says oxygen gas is at a temperature of 40 degrees Celsius when it occupies a volume of 2.3 liters. To what temperature in Celsius should it be raised to occupy a volume of 6.5 decimeters cubed? Decimeters cubed is equivalent to liters. So 6.5 decimeters cubed, this also equals 6.5 liters. Okay, so be mindful of that as you're going through. With the Celsius, we need to convert to Kelvin and then convert back. So I'll give you an opportunity just to finish working on that, then we'll go through the answer. All right, so by now you should have had a little time to work, and like I said, you should have first converted our 40 degrees Celsius to this 313 Kelvin. So we have our V1, which is our 2.3 liters, over our 313 Kelvin, equals our V2, which is 6.5 liters, over our T2. If we cross multiply and divide, we get 884.6 Kelvin, which when we convert it is 611.6 degrees Celsius. I only have a couple videos left. For this video, we actually have two videos that go along with it. So the first one, you're going to see what happens to a soda can as the air inside is first heated up and then cooled very quickly. And the second one, you're going to see what happens when a pressurized tanker loses its pressure, or it has a decrease in temperature, and you're going to see what happens then. It's pretty interesting. So to sit back and watch this, once again, be thinking about what's happening to the temperature and pressure during these videos, and focus your drawing on what happens to the can, not the tanker. Okay, so watch the next two videos, then we'll come back together here. All right, so during the videos, like I said, we saw that the can was crushed and the tanker was crushed. Now we want to explain why that happened. So if we take a look, this is what our drawing should look like for this. So in our can instance, what we did was initially heated up all the molecules in the can. So if you look over here, we make it so our atmospheric pressure and our pressure inside our can are equaled out. And the reason it's able to do that is because our can's open on top, right? So some of the molecules can escape, leaving the pressure to be equal to the atmospheric pressure. Now, on this side, what we do is submerge the can face down. And we do this because now we're closing off the environment. So none of the gas, no new gas can get in. Okay, and we are severely decreasing the temperature of the can, which in turn decreases the pressure. So now it's not able to push out hard enough and the can collapses. The same thing's happening with the tanker. This is a perfect example of Gay-Lussac's law. The equation that goes along with it is P1 over T1 equals P2 over T2. And once again, we have a problem to go through here. It says the inside of a metal gasoline tank is cleaned with hot steam at 100 degrees Celsius. The pressure inside the tank is 1 atmosphere. Workers accidentally seal the tank when cleaning is completed. When the tank returns to room temperature, what is the final pressure in torr inside the tank? Okay, so two things here. We need to make sure that we use our temperature in Kelvin to start with. So up by the hot steam, we want to convert that. So we have 1,273 Kelvin. And we want to convert our final temperature from 25 degrees Celsius into Kelvin. Okay. All right, so let's take a minute, try and work through the problem, and then when you come back, I'll go through the answer with you. Okay, so now we're back. We had initial pressure, we said, of 1 atmosphere. We converted our Celsius to Kelvin, so we have 1,273 Kelvin initially, and then 298 Kelvin to end with. Okay, so we took 1 times 298 and divided by 1,273 Kelvin, giving us a pressure of 0.234 atmospheres. The problem says, though, we want to end in torr, so we had to convert into torr. So we wrote 1 atmosphere on bottom is 760 torr, and then we multiply that out to get 177.9 torr over here for our answer. So once again, we just are doing a conversion after we're over here because we want to know what the pressure is in torr. Now we'll be moving on to our very last demonstration. The last video is very interesting because now we're actually combining all of our gas laws into one. So we're going to be seeing what happens as we change pressure, volume, and temperature. And this one's called a fire syringe demo. And the reason that, well, I don't want to spoil the video for you, but we'll talk about what happens after you're done watching the video. So why don't you pause right now and take a look at the fire syringe demo. All right, welcome back. Now, during the fire syringe demonstration, we saw that the cotton ball actually lights on fire a little bit. Now, this isn't because we had special tricks like flint or anything like that in the bottom of this container. What's happening here is that we're actually, by decreasing the volume, we're increasing the pressure so much that the temperature also increases greatly, which lights the cotton ball on fire. So, if we take a look here, this is somewhat of what your demo should look like. So in the bottom here we have some cotton and a few gas particles, and now we're greatly decreasing this volume in a short time here, which greatly pressurizes the container and raises the temperature enough to make fire here. This was an example of the combined gas law. And the combined gas law equation is P1V1 over T1 equals P2V2 over T2. And then our very last problem says you have a 2.4 liter container of air at STP. From out of nowhere, Bigfoot stomps on it, decreasing the container's volume down to 0.5 liters and increasing the pressure to 8 atmospheres. How hot in Celsius is the air in the container now? And one thing I want to point out here is that the container is at STP. So remember, that's 273 Kelvin. All right, take a minute, work with the people around you, and we'll come back and we'll answer this one together. Okay, so if we're going to plug this into our P1 times V1, we would have that 1 atmosphere times 2.40 liters. That's our initial pressure and volume. And we are multiplying that by, dividing that by our initial temperature of 273. And that's going to equal our final pressure, 8 atmospheres, times our final volume divided by T2. To solve this problem then, what we need to do is take 8.0 times 0.50 and cross multiply that with 273. So we'll take 8.0 times 0.500 times 273, and then we are going to divide by 2.40 and divide by 1 to get our final temperature. And that's going to give us a temperature in Kelvin. So we're going to get 455 Kelvin. And if we convert that back to Celsius, we'd find out that the container gets pretty darn hot. It's all the way up to 182 degrees Celsius. That's all I have for you guys today. Hopefully you enjoyed the demos, and I will see you back in class on Monday for our gas laws stations.